Dear students, let us study law of conservation of momentum now, as we have already studied in the previous chapter about system of particles. For a system of particle we have studied that velocity of center of mass of a system of particle can be given by total momentum of system divided by sum of mass of all particles. Similarly, we have studied that the acceleration of center of mass of a system of particle can be given as net external force acting on the system divided by mass of all particles of system. Now in this situation, if we just follow a sequence like if on a system of particle F external is equal to 0. That means no external force is acting on the system of particles. That means if no force is acting on the system, the acceleration of system of particle is equal to 0. Now if acceleration of center of mass is 0, this implies that the velocity of center of mass remains constant, obviously, as no acceleration implies no change in velocity. Now if velocity of center of mass is constant, this means the momentum of system remains constant. So indirectly we can also state that if no external force is acting on the system of particles, that means the total momentum of the system remains constant. This concept is called law of conservation of momentum. We just define this in language also. If on a system of particle no external force is acting, the total momentum of system of particle remain conserved. So if no external force is acting on system of particle, the total momentum of system of particle remain conserved. So indirectly, momentum remains conserved if no external force is acting. This is called law of conservation of momentum. Let us see some basic examples based on law of conservation of momentum. As we have just now seen, that, if no external force is acting on the system of particles, that means if F external is 0, this implies that the system momentum remains conserved or constant. Just now we have seen, and this we term as law of conservation of momentum. There are many examples based on this fact. Like the simplest example to understand it is recoiling of a gun. This you might have studied in your earlier classes also. Like say we are given with a gun. And say, if gun fires a bullet. Now in this situation bullet is fired by the gun because of the internal forces. A bullet plus gun system. In this situation, if the bullet is fired with net velocity Vb, certainly the bullet is gaining some momentum. And to gain some momentum we can state, in this situation, gun must also gain a momentum in backward direction. Because we can say, before firing, momentum of the system was 0. If we talk about system momentum, because both bullet and gun are at rest. Now if the bullet gained some momentum, the gun should gain some momentum in opposite direction, so that the total momentum remains 0, and momentum is a vector quantity. So in this situation, if mass of gun is capital M and mass of bullet is small m, we can simply state by conservation of momentum, we write before shot the momentum was 0, and this must be the momentum after shot. So we can write after shot, the bullet will have a momentum small m into velocity of bullet. The gun is having negative of capital M into velocity of gun because, it is taken negatives due to its opposite direction, which gives us m into Vb is equal to capital M into Vg. Now this relation is also basis of many various kind of problems related to conservation of momentum. Let's see another example for adding a mass on a moving mass. This is also a very common basis for various kinds of problems. Let's say we have a block of mass m1 moving with speed v0 during its motion. Say on this block of mass m1 another block of mass m2 is gently dropped onto it, and it is dropped in such a way that due to friction m2 will stick to m1. So obviously after this point, both these blocks will move together when this m2 is added to m1, and, obviously, as no external force is present here. As no external force is there in the system, we can say that the total momentum of system remains conserved, so the final speed of system changes, say it changes to Vf. Now in this situation we can simply state that by conservation of momentum, we use initial momentum before adding the mass m2 with m1. The momentum was m1 v0, and the final momentum after addition can be written as m1 plus m2 into Vf. So this will help us in calculation of final velocity. We can simply write final speed of blocks, combined blocks, is, which can be written as Vf is equal to m1 v0 upon m1 plus m2. This is the way how we handle such type of situations.